Hi, welcome to CBA Office Hours. This is an online forum where Patrick Curran and I talk about statistical methods and issues that arise in behavioral health and social sciences. Today what I'm going to be doing is extending our series on the linear regression model. In previous episodes we've looked at the simple linear regression model with a single predictor, and that's really useful for understanding the foundations of the regression model. What's the model all about? How do we obtain estimates using ordinary least squares? How do we make inferences in the model from the sample to the population? But it is less useful from a practical standpoint because in practice we tend to have more than one predictor of interest. And so what we're going to do today is extend the simple regression model to a multiple regression model where we include multiple predictors simultaneously in the model and assess the effects of each predictor in the presence of the others. What I'm going to do is I'm going to begin by just kind of showing what this looks like in terms of the equation for the model, but I'm going to very quickly talk about the motivations we have. I'll turn from the equations to the motivations we have for using this model in practice and some of the power that it brings us, the conceptual power that it brings us in terms of being able to understand the effects of our predictors. Then after that, we'll consider a demonstration using some real data and see sort of a walkthrough of what a multiple regression analysis might look like and how we would interpret the estimates that we obtain from that analysis. So first off, let's just think a little bit about what is the multiple regression model. And I'm going to start out with the simple regression model and build from there. So in our simple regression model, we have our outcome variable is equal to an intercept plus a slope times the predictor plus some residual, right? And so we might, for instance, be looking at y might be the success of children in grade school, and x might be parental involvement, maybe number of hours spent in school-related activity per month by the parents or something like that. And so we have a single predictor of interest in the model, and we obtain our estimates, our intercept and slope estimate from the model, and those tell us what the regression line looks like. And so we have our x variable, we have our y variable, and there's some relationship between x and y that is captured by that regression line, and the regression line is given by beta naught plus beta 1x. And then any given individual, their observation is not going to be exactly on the regression line, right? And so the residual is that deviation of the observation from what we might otherwise expect it to be from the regression line. All right, so that's with a single predictor in the model. Now, it looks like a fairly trivial extension to move to the multiple regression model. And so all we're going to do, right, is let's just add a second predictor. All we're going to do is we'll call that x1 now, is we're going to add beta to x2, and then we've got a residual. So now we might be looking at success in school as a function of parental involvement, as well as, I don't know, maybe number of books in the home, maybe as a marker of educational enrichment. And so we've got two predictors in our model now. And so if you're a geometric thinker and you've been thinking in terms of the regression line, now we've got not a regression line, but a regression plane. And so we've got x1 still, right? But now we also have x2. And any given individual's expected value, predicted value, will be a function of both x1 and x2. And so whereas we had a line before, now we're going to have a regression plane, right? And so I'll try to kind of make that look plane-like. Right, so we're going to have a regression plane. And for any given individual, right, they've got some level of x2, they've got some level of x1, we'll say their x1 is over here, and so we would say, all right, their particular configuration of x1 and x2 places them right here. Now we're going to travel up to the regression plane, and we might say that might be this point right here on the plane, and that would be our expected value for that person. Now their particular observation might not fall directly on the plane, and so again there's going to be some residual, and just like we do in the single predictor case, when we estimate the model, we're going to use ordinary least squares, and we're going to try to find the regression plane that minimizes those residuals, minimizes the sum of the squared residuals. So we can see that geometrically with two predictors. It's a little bit harder moving to 3 or 4 predictors, but the math is pretty straightforward. Is if you want to have a third or a fourth predictor, right, you just go ahead and tack those on, and so we're going to have beta 3x3 and beta 4x4 and so on, and then the residual, of course, is what is left over. All right, so that is the multiple regression model. So it's a fairly straightforward extension of the simple regression model. We're simply going to add some more predictors, and we're going to get a regression slope associated with each one of those predictors. All right, so what makes the multiple regression model so powerful? Why do we find this model so attractive? Well, there are a variety of reasons. One reason is that most of our outcome variables of interest are multi-determined, right? And so the multiple regression model gives us the opportunity to incorporate multiple determinants of an outcome simultaneously into the model. All right, so related to that is that when we bring more predictors into the model, predictors that are informative about the outcome, then we can enhance our predictions, right? So we can make our predictions better. We can drive up our model R-squared, the explained variance in the outcome. So whereas parental involvement might predict some variance in school success among children, incorporating also number of books within the home, incorporating also family income, maybe also incorporating some measure of preschool exposure, that all those things might be determinants of success in school, and by including all of them we can drive that R-square up and explain more variance and success. All right. Also related to that, you hear an airplane going overhead, also related to that is that when we push the R-square up, the unexplained variance shrinks, right? So we're explaining more variance, the unexplained variance goes down. And so our mean squared error in our regression model decreases, right? That's our estimate of the residual variance, is the mean squared error. And remember, when we did some earlier episodes on inference, the mean squared error goes into the computation of the overall model F-test, and it goes into the computation of the t-test and confidence intervals for individual regression coefficients. So if we can make that mean squared error smaller, we can often increase our power. So make it more likely that we would find significant F-tests and t-tests for our regression coefficients. And that's particularly true when the additional predictors that we add to the model are not too redundant with the predictors that are already present. Right? So if we add in a predictor that's relatively unrelated to the predictors that are already present, but is related to the outcome variable, then we push that mean squared error down and we can augment our power. The most common example of that is when people include a pre-test measure in a regression model where you're predicting a post-test of the same measure and then evaluating some kind of treatment or intervention effect. Is that pretest is going to be uncorrelated with treatment because treatment was randomly assigned, and so you're going to have no relationship between the predictors, but each predictor may be related to the outcome. You can shrink the mean squared error and enhance your power to detect the treatment effect. Right, so that's one example of where having multiple predictors in the model can enhance power. But far and away the biggest reason why we like the multiple regression model is that it allows us to get statistical control. Statistical. You'd think I could spell that. Statistical control when we have potentially confounding variables that we need to take into account. And so, for instance, if we're trying to predict success in school as a function of parental involvement, well, what about family income? Family income might be an important predictor of success in school, but it might also be related to parental involvement, right? As maybe families that have more income also have greater resources to be present at the school or to be involved in school-related activities. Right, so there's some relationship there that we need to take into account. So we want to see what is the effect of parental involvement, but parental involvement is related to family income, and family income might be related to success in school for all kinds of other reasons. Right? It might be related to success in school because of the kinds of schools that those families can place their kids in, or because those families can afford more extracurricular activities or more enrichment activities, or etc. Right? So you get the idea, is that often when we have multiple determinants of an outcome, those determinants are related to one another, and we may want to control for one or others when assessing our predictors. Right? So we may want to control for family income when assessing the effect of parental involvement. That's kind of hard to do experimentally. right, is it's very difficult to be able to control everything experimentally, and it's kind of hard to do through sampling. We can't just sample a whole bunch of people who have exactly the same family income. But we can, in the regression model, get a sense of what would be the effect of each predictor while holding all others constant. They're not literally constant, they're varying in the sample that we're collecting, but we can estimate what the effect of each predictor would be while holding all others constant, or controlling for those other predictors. All right, so let's explore that idea a little bit more of statistical control and how to obtain estimates for each predictor controlling for all others. And so again, we're going to go back to that single predictor regression model as a jumping off point. And so in the single predictor regression model, the expected value of the outcome is just beta naught plus beta 1x, right? It's just that regression line. And so we've talked previously about how do we interpret these parameters. Is the intercept is the expected value of y when x is 0. When x is 0, that drops out, and we're left with beta naught, and so our intercept is the expected value of y when x is 0. So it might be the expected success in school for a kid whose parents just aren't involved at all, right? And then our slope, we get our slope interpretation from comparing values of x. It conveys the effect of x and how x produces differences in y. And so we can consider two values of x. So let's consider a value of x equal to, we'll just say a. A might be 5, it might be 10, but whatever it is. And then we'll consider a value of x equal to a plus 1. All right, so 1 unit higher on that particular predictor. All right, now we're going to get beta naught plus beta 1a, and here we're going to get beta naught plus beta 1a plus 1. And notice what's going to happen if we take the difference between those two things is the intercepts are going to cancel, and a of the beta 1s are going to cancel, and what are we left with is just beta 1. So beta 1 then is the change in y, or the difference in y, that we would expect to observe as a function of a 1 unit difference in x. Right? So that's our interpretation in the simple regression model. So we could do a regression where we look at success in school, we predict it by parental involvement, we get our beta 1. Our beta 1 tells us for a 1 unit change in parental involvement, what do we expect to see different in success in school? How much is that going to change? All right, so that's just sort of a review of the one predictor case. But now let's see what happens when we add another predictor, because the problem with that model, of course, is that that effect of parental involvement might be confounded with the effect of some other variable like family income. So I'm going to now add x2, that's going to be my family income variable, into my model. And now let's see how our interpretations change. Is the intercept turns out to be interpreted very similarly. Is if we set both predictors to 0, then not only does that term go away, but that term goes away too, and we get beta naught. So our intercept is always our expected value for our outcome when all predictors are 0. So this would be for a kid whose parents are not involved and whose family has no income. Right? Might be an extrapolation, might not be in the range of the data, but that is our interpretation of our intercept. And we can move things around our data to make that intercept more interpretable, but for right now we're going to focus mainly on the slopes. And so let's think about what is the effect of x1, right? So what is beta 1? Well, that's my effect of parental involvement. And I'm interested in what is that effect of parental involvement holding constant family income. If I could select a sample where everybody had exactly the same family income, right? An impossibility, but just imagine it. You could select a sample where everybody had the same family income, then you'd still have variation in parental involvement, and you could see what exactly is that effect of parental involvement, right? It would be uncontaminated, unconfounded by any differences in family income because you've held them all constant. Well, the regression model allows us to get an estimate of what that would be even without literally holding everything constant, right? So we can get an estimate of the effect of parental involvement holding constant family income even though there's variation in the data. All right, so what we're going to do is we're going to say what's the expected value of y at 2 different levels of parental involvement while holding constant family income. All right, so let's start out with parental involvement being set to A and family income being set to a constant we'll call C. All right, then what are we going to get? We're going to get beta naught plus beta 1 times A plus beta 2 times C. All right, and then we can do the same thing but now incrementing x1 up 1 unit. So a 1 unit increase in parental involvement. But we're going to hold x2, family income, still constant. And we get beta naught plus a plus 1, oops, a plus 1, beta 1s plus beta 2c. And notice what's going to happen is, again, we're going to have some things cancel. So the intercepts are going to cancel out, a of the beta 1s are going to cancel out, and here's the important part, is b2c drops out too. So we're holding constant family income, we get beta 1. The expected change in y for a 1 unit change in x1 holding constant x2. So the expected difference in success in school for kids who have a 1 unit difference in parental involvement, but holding constant their family incomes. Right? That's the powerful thing about multiple regression, is that we don't necessarily have experimental control or the ability to kind of select everyone to be equivalent on some confounding variable, but we do have the opportunity to do statistical control. And so we can see what are the effects of each predictor controlling for the other. So beta 1 is the effect of x1 holding x2 constant, beta 2 is the effect of x2 holding x1 constant. And if we were to add other predictors, we would simply say holding all other predictors constant. Okay? All right, so that's kind of just walking through a little bit of the algebra. There's also a nice way to kind of visualize this in terms of variances of variables. And so we'll also look at that, and that will give us some additional insights into this idea of statistical control. So I'm going to represent the variance of x1 as a circle. So this circle represents all the variability that exists in this variable. And so that's my parental involvement variable in our example. And then I'm going to represent family income with another circle. So that's my x2 variable here. And notice that I've drawn the circles to overlap. That's the relationship between these two variables, that perhaps families that have higher income also tend to be more involved. Right? And so there's some area of overlap where those predictors are related. There's some redundancy in the information that those predictors provide. Now I'm going to draw on my outcome. Right? So there's my school success outcome. And notice that there's 3 areas that represent variance that we're explaining in our outcome as a function of our 2 predictors. So we have this area here we'll call A, that area we'll call it B, this area we'll call C. All right. C is interesting because C is variability in school success that could be predicted by parental involvement, but could also be predicted by family income. Right? So it's not unique to either predictor. It could have been explained by either predictor. And so in the multiple regression model, we're going to get an overall model R squared that's going to be equal to A plus B plus C. That's all the variance we can explain in Y. But part of that is common. It's shared. It could be explained by either predictor, and part of it is unique to each predictor. So this part over here, A, is what we're getting at when we get beta 1. All right, that's the unique effect of parental involvement controlling for net of partialing out family income. You see a variety of language used to describe it. And then B2, or B, is going to be our beta 2, right? That represents beta 2. So that's the unique effect of family income controlling for net of pulling out any variance associated with parental involvement. Right, so we're going to get an overall model R squared that's A plus B plus this C, but then we're also going to get these unique effects that are just the A and the B part, so the part that is unique to each predictor alone. And so that's a really cool thing about the multiple regression model. Now another thing we can do, in addition to getting our estimates of beta 1 and beta 2, is we can get standardized estimates. There are a variety of ways of getting standardized estimates. There are standardized regression coefficients, there are partial correlations, semi-partial correlations, etc. But my favorite is the squared semi-partial correlation, sometimes abbreviated SR square. And what that represents is it takes this beta 1 and this beta 2 and it standardizes them into the same kind of metric as R square. And so it gives you the percent of variance explained. And you'll get an SR squared for x1 and you'll get an SR squared for x2, and that represents the unique variance explained by each predictor. So the A part and the B part, respectively. And of course, if we had 3 or more predictors, it would just extend from there. And again, we would have what's the effect of each predictor holding all others constant. Now, because we are partialing out the variance associated with other predictors, we're pulling out the variance of x2 when looking at the effect of x1. You'll often see these regression coefficients referred to as partial regression coefficients. You'll sometimes hear them described as unique effects. I like to say it's the effect of x1 controlling for or holding constant x2. But bear in mind that's a little bit different interpretation than if you only had x1 in the model. If we only had parental involvement in the model, A plus C would be what we would get for our effect of parental involvement, but the C part is actually confounded with family income. So that's the advantage of moving to the multiple regression models. We can pull that part away and say what's the unique effect of this predictor holding constant all others. All right, so hopefully that gave you a pretty good idea of what the multiple regression model is, what it's all about, how you can leverage this power of the model to get at statistical control and multi-determined outcomes. Now what I'm going to do is turn to a demonstration and sort of walk you through how this works in practice in a real data analysis.
This is the data we're going to be analyzing. We're going to be predicting murder rates, variation in murder rates across states in the United States, also including the District of Columbia, as a function of the percent of the population with a high school diploma, the percent living below the poverty line, and the percent living in metropolitan areas. And you can see there's a fair amount of variation in murder rates. At the time this data was collected, and I don't recall exactly what year that was, the murder rate in Louisiana, for instance, was 20.3 individuals per 100,000, whereas the murder rate in Kentucky was 6.6 per 100,000. And so we see a variation there, and we want to see whether or not we can explain that variation in murder rates as a function of education, poverty, and kind of the density of the population, how much of the population lives in city-like areas. So we have data here for all 50 states, plus the District of Columbia. Now notice that the District of Columbia has somewhat unusual values for these predictors. It is entirely metropolitan, it's really a city, and then you see it has a very high murder rate relative to other states and so forth. And we'll see that also is that whenever you do a regression analysis, you'll probably want to do some initial exploratory graphical data analysis to get a sense of what's going on in the data, and we're going to do that with a scatter plot matrix. We'll see DC will jump out in that as well. Here we've looked at scatter plots and histograms for all the variables in the model, and you can see that in the histogram for murder rate, DC really stands out as very high relative to the states, and then in the scatter plots as well we see it popping up as an outlying observation. So just a reminder, it's always good to look at your data before jumping into analyses. If we were to include DC in our multiple regression models, it would have a fairly high influence on our parameter estimates because it is has such unusual values. So we're going to restrict our analyses to just the 50 states. We can look at a new scatter plot matrix, removing DC, and you can see that things look much more regular here, no particularly outlandish observations. And you can see that murder rate appears to be related to high school graduation rates. So the more high school graduates, the lower the murder rate. Related to poverty, higher the poverty level, the greater the murder rate, and it looks like also somewhat related to percent metropolitan. The greater the density of the population, the more the population is condensed into metropolitan areas, the higher the murder rate as well. So this is a good example of how we might use multiple regression to get at multi-determined outcome variables, as murder rates may be a function of all 3 of these things, not just one, and so we may want to use a model that includes all 3 predictors. It's also a good example of how we can use the multiple regression model to account for the relationships among our predictors. And so for instance, you can see that high school degrees and poverty are pretty highly related to one another. That's this cell right here, where you can see that the higher the higher the number of high school graduates, the lower the poverty level, and vice versa. So we see that some of these predictors are fairly related to one another, and we can use the multiple regression model to see what is the effect of high school graduation holding constant poverty or vice versa. And so we'll do that in our analyses. We're going to start out with a model where we only use high school graduation rates as a predictor, so just a single predictor model. And I'm conducting these analyses in SAS, but you would get the same results if you were to use Stata or SPSS or R or any other statistical package. But here we get the results for that single predictor model. We see our R-squared is 0.33, so we're explaining about a third of the variance in murder rates across states as a function of percent high school graduates. We do get a significant overall model F test, indicating that we're explaining more variance than might occur just by chance alone. We are going to focus on our slope estimates in these models. So here's our percent high school graduates. We get an estimate of -0.4. So for each 1% increase in the number of high school graduates, we see a 0.4 per 100,000 individuals decrease in murder rate. And that is statistically significant. Now remember, your test of the slope and your test of the model are redundant with one another in a one predictor case. In fact, you could take that t statistic, -4.90, and square it, and you get 24.04, and you get exactly the same p-value for those two tests. That only happens in the one predictor case. We'll see those pull apart when we incorporate additional predictors. We're not going to focus too much on the intercepts in these models because they're not terribly interpretable. They're just sort of pegging down the regression line. That intercept of 38.5 would literally be the murder rate in a state that has no high school graduates. But of course, that's a pretty extreme extrapolation from the actual data that we have. Every state has a much higher high school graduation rate than 0. So we're not going to focus too much on intercepts. We're going to focus instead on slopes. I'm now going to incorporate poverty as a second predictor into this model, and we'll see what happens. So now my R-square has jumped up. It was 0.33, now it's 0.42, so I'm explaining some additional variance as a function of incorporating both high school and poverty into the model. I again have a significant overall model F test. This is a test of the model as a whole, so it's a joint test of both predictors, percent high school graduates and percent in poverty, and you can see the degrees of freedom now are 2. We've got 2 predictors going into the model. And then we can turn to our t-test of the individual predictors to see which predictors have significant unique effects, and what you see is that the effective high school graduation rate is now no longer significant. So controlling for poverty levels, high school graduation rates do not have a significant effect on murder rates. The dominant factor here is poverty. Per 1% increase in the number of families living below the poverty line, we see a 0.4 per 100,000 increase in murder rates, and that is statistically significant. So that's looking at 2 predictors. How about if we put all 3 predictors in the model? So we'll now add percent metropolitan. We now have 3 degrees of freedom for our overall model F test. And you can see again it's statistically significant, so the joint test of the 3 predictors is significant. It doesn't tell us which predictors are doing what, but it just tells us that overall our model is predicting more than just chance murder rate variation across states. We see our R-square is a little higher still. We're now explaining about 59% of the variance in murder rates across states. And then our estimates, we come down here and we see that high school graduation rates, again, not a significant predictor. Poverty remains a significant predictor, and percent metropolitan is also a significant predictor. So per 1% increase in poverty, we see now a 0.56 unit increase in murder rates when holding constant high school graduation rates and the percent of the population that lives in metropolitan areas. For percent metropolitan, we see a 0.08 roughly increase in murder rates per percent of the population that lives within a metropolitan area, holding constant poverty and high school graduation rates. So you're treating your other predictors as constants when evaluating the predictor of interest. Right? So those are the raw regression coefficients. We can also, if you desire a standardized measure of effect size, my personal favorite is the squared semi-partial correlation. I'm going to add those on here. We see those right here. And what they tell you is the contribution each predictor makes to the overall model R square. And so you can see that percent high school graduations of high school graduates is explaining very little of the variance in murder rates on its own uniquely. Percent in poverty is explaining 14% uniquely. Percent metropolitan is explaining 17% uniquely. If you add those up, you will not get the overall model R-square because those areas of overlap are being excluded. These are the semi-partial squared correlations are the unique variance explained by each predictor, but there is some shared predicted variance as well. And so your overall model R-square will typically exceed the sum of those squared semi-partial correlations. But they are a nice way of trying to get a sense of which predictors are explaining the most variance in the model. And you can see that percent metropolitan is explaining the most. It's at 17%, whereas poverty is explaining 14%, and high school graduation rates are really not factoring in much at all once we control for poverty and metropolitan. As remember, we originally identified a significant effect for that when it was the only predictor, but that was not then controlling for poverty or metropolitan. Once we put those variables into the model, we see that high school graduation rates no longer exert a significant effect. Whatever effect we had observed before is entirely redundant with the effects of poverty and metropolitan.
Well, thanks for joining me for this episode of Office Hours. I hope that it gave you a good sense of the multiple regression model and how you might use it in practice. Now that we've built out the architecture of the multiple regression model, we can, in subsequent episodes, consider some other topics, such as how to include categorical predictors in the multiple regression model, or how to include interactions in the multiple regression model. So hopefully you'll join me again for those topics, but for right now, I'll see you next time. Thanks.